Hello, we are happy to present our work Escape, Equivariant Shape Completion via Anchor Point Encoding. To achieve rotation equivariant point cloud completion, existing point cloud completion methods fail on completing transformed inputs. This is because they utilize point coordinates while training and rely on canonical coordinate frames. Many agents operate on dynamic environments without access to canonical coordinate frame. Therefore, building a point cloud completion method independent from canonical frame is crucial. We propose our rotation equivariant point cloud completion method, Escape. It achieves rotation equivariance with the help of its three components. First, rotation invariant anchor point encoding. Second, rotation invariant attention base point transformer. And finally, point coordinate optimization. To obtain a rotation invariant representation, we relied on pointwise Euclidean distances. We build our features as 1. Select a set of points along the 3D shape as anchor points using farthest point selection, FPS. To obtain a rotation invariant representation, we relied on pointwise Euclidean distances. We build our features as 1. Select a set of points along the 3D shape as anchor points using farthest point selection, FPS. 3. Improve each anchor to another point with a higher curvature value. And 4. Build point features as distances to all anchor points to construct DP. Constructed point features are used to train a transformer model that learns to complete 3D shapes in our feature domain. Our network takes point anchor distances for the partial shape and learns to predict all point anchor distances for the complete geometry of the same shape. Predicted point pairs for the complete geometry transform back to the 3D coordinates with the final optimization step. Given distance predictions and coordinates of the anchor points, this step finds the optimal coordinates of the complete points by solving the following optimization problem. We evaluate our method on well-established datasets: Point Cloud Network dataset, Kitty Cars dataset, and Omni Object dataset, which we purposed the first time for point cloud completion. To compare existing methods, we created two setups. We trained existing methods with rotation and translation augmentation. We normalized the inputs with condors and feed to completion networks for inference. In testing time, we randomly applied rotation and translation to the inputs on each 3-dimension. Compared with the both evaluation methods, Escape achieves superior results nearly all categories in PCN dataset. This is also depicted in visual results. Predictions of existing methods are subject to high noise and structural deformation. On the other hand, Escape can yield equivariant predictions under rotation, superior to all other methods. This makes Escape applicable to scenarios that require non-canonical point processing. Similar to PCN, Escape achieved the best results on transformed inputs in Omni Object dataset. Qualitative results in Omni Object dataset depicts Escape's performance against existing methods. While partial objects in this dataset subject to less missing regions, existing methods fail to complete object geometry on rotated inputs. Whereas Escape yields the same prediction even the inputs are rotated or translated. In summary, we proposed Escape, a novel rotation equivariant 3-dimensional encoding strategy using high curvature anchor points, enabling robust shape description and reconstruction. We present an end-to-end rotation equivariant shape completion method, demonstrating robust performance under arbitrary rotations and in the absence of canonical object coordinates. We establish and evaluate a challenging real-world shape completion benchmark using the Omni Object dataset, featuring partial point clouds with diverse geometries and arbitrary poses, bringing shape completion works to real-world data.